My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Adda and School of Astrophysics and Astronomy and YouTube channel Pretam Kumar, I'd like to welcome you all to our International Physics webinar. So hope you are well and safe from Corona pandemic. So good evening to all here in Bangladesh and a very good morning to all those who are watching this program live from USA. So today it's our 168th International Physics webinar. So I think you have already come to know that the Department of Physics, Pabna University of Science and Technology has started its online program, including International Physics webinar. So it's very difficult for us to continue our normal academic program inside the campus due to the Corona pandemic. So we have to start our online program. So we're trying with this new normal situation. So I think our students have learned a lot of things with this series of webinars that we have started last year in June 2020. So today it's our 168, and today I would like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, University of Nebraska, Lincoln, USA. And we have with us here today Dr. Christian Binek, sir, Charles Bessey, Professor of Physics, Director, NCMN, Department of Physics and Astronomy, University of Nebraska, Lincoln, and he has already connected with us. So I'd like to welcome our speaker, sir. Good evening and good morning to your part, and thanks for accepting our invitation, sir. So we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. So for those who are new, I'd like to inform you all that we have divided our webinar into three parts. First of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver his speech. And at the end, we have a discussion session. In that time, anybody can join with us, and you can ask question by commenting also. So I think we have already come to know the title of this today's International Physics webinar. Title is the Voltage Controlled Nil Vector Rotation in Zero Magnetic Field, and our speaker is Dr. Christian Binek, sir, Charles Bessey, Professor of Physics, Director NCMN, Department of Physics and Astronomy, University of Nebraska, Lincoln, USA. And we can see his educational background. You can see he completed his elementary school in 1975 and his secondary school in 1984, and then his graduate in completed his graduate degree in physics in 1990 and his PhD degree in 1995. And he worked as a postdoctoral fellow from 2001 2003, and then he joined as an assistant professor at the University of Nebraska in 2003, and he worked there up to 2009 as an assistant professor, and then he joined as a assistant professor in 2009, and he worked as a assistant professor up to 2015, and then from 2015 to present situation, he is working as a professor of that department. So our professor Charles, so he's also a professor of Charles Bessey, professor of the Department of Physics and director of the NCMN, Department of Physics and Astronomy, and also a director of the Nebraska Center for Material Science and Nanoscience, director of Nebraska Nanoscale Facility, National Nanotechnology Coordinated Infrastructure, and director at the Emergent Quantum Materials and Technology. We can see his research interest exchange bias in the magnetic metal insulator hetero systems and matrix insulated magnetic nanoparticles, experimental approach of fundamental aspect of statistical physics, and this is honors and fellowship and awards. This is his patent list and publication list. We can see his research get ID. His research point is 114.23.23. This is huge number. So this is his books and chapter list. So thanks for all of your patience. Now it's time to go to our speaker. So sir, thanks again for joining with us, and thanks again for accepting our invitation, sir. It's your time, sir. You can start your session.
All right. Thank you, Professor Das, for these kind words and for the opportunity to speak here in this nice webinar. Actually, I saw already a couple of very interesting talks here myself.
Thank you, sir. It's my pleasure, sir.
Very nice. Okay, I think I start sharing my screen then.
Okay.
if that
Minimize it, yeah.
can you see the presentation?
Yes, yes, sir. We can
All
see.
right.
You can start.
Then I get started, and because the subject I present today is maybe a little bit specialized for some, let me first, before I really dive into it, give you a broader picture of what is this about. So as you know, we are enjoying all the advances of Moore's law in terms of microelectronics, and everyone has heard that the progress may come to a halt there because of fundamental physical challenges, and we need new switches, new ideas, new concepts to keep that progress of exponential cost to performance ratio improvement running. And spintronics is one of the candidates that can solve this problem and can be potentially be outperform CMOS electronics, which has been so successful in scaling. Now, part of spintronics is the modern aspect of antiferromagnetic spintronics, and and in particular voltage controlled spintronics, and that's the field where I work in, because one of the big bottlenecks is energy consumption, and we want to keep the energy consumption at a minimum. Now, it turns out in spintronics, many people try to switch magnetic states as switching between bit states of 0 and 1. They switch them by electric currents, either unpolarized or spin polarized electric currents. That is, from a physics perspective, a neat thing to do, but it is power consuming, and it is and whenever a current is flowing, you have a joule dissipation typically and heating, which is then detrimental to the device itself. Now, voltage control, that is the first term in this title, means really we switch a magnetic state, in this case the magnetic state of an antiferromagnet, not a ferromagnet, and we do that without current, just with voltage. Now, I work on this for a long time and use so-called magnetoelectric materials to do that, and I will say a few more words about this. But one catch of all this has always been that if I want to take a particular textbook magnetoelectric material and switch its antiferromagnetic spin structure from one orientation to the other, I have to have a magnetic field present. And that is because the magnetic field breaks time inversion symmetry. And by switching an order parameter that is odd under time inversion and doing that with a field that is even under time inversion, that's not straightforward. So I always needed a magnetic field. And what I report today is progress we made to voltage control an antiferromagnetic state in zero magnetic field. That is very exciting for applications and of course also fundamentally. And what makes this more exciting is the fact that we can do that at and above room temperature. So right along the alley of applications. So that was a rather lengthy introduction of the title, but I think it's necessary to put this in a broader framework. So what I do here a little bit, I take you on a journey that took us a long time, more than a decade, to get to where we are. And we started out by doing this Néel vector switching, 180-degree rotation, in so-called exchange bias heterostructures, where one part of the heterostructure was this magnetoelectric antiferromagnetic materials. So that is an important background piece of information, but then I will report on what is the disadvantages of this approach and why we gave up on this. Then I talk about doping this magnetoelectric antiferromagnet with boron and what that does. And then I show you those results, those switching results on Hall bar type devices, where we can achieve 90-degree rotation of the Néel vector in zero magnetic field just by voltage. And because this is such an interesting result, it's a big claim, so to say, and it requires a backup. And I show you independent evidence that this switching mechanism is indeed switching, magnetic switching, and not an artifact. We do that by magnetic force microscopy, and then I conclude. So let me get started with a brief introduction on voltage-controlled exchange bias with magnetoelectric antiferromagnets. And even one step before, let me give a brief introduction, and everyone who is interested in the physics of magnetoelectrics may enjoy this. So a very brief introduction into the magnetoelectric effect in this particular material, Cr2O3 chromia. So here you see a fraction of the unit cell of this material. This is the easy axis or C axis of the material. It's a threefold rotational symmetry axis. And here you see the chromium 3+ spins in red. The full magnetic unit cell has 4 of them. I show you here just 2 for simplicity, down and up orientation of the spin. Now that chromium 3+ ion sits in a nearly octahedral in an environment of oxygen 2- ions, which has almost octahedral symmetry, but some distortion, as you can see here, that is indicated by these triangles. This one is a bit bigger than this triangle of oxygen 2- ions. And now we can ask, what happens if I expose this material to an electric field? And to keep it simple, the electric field here is applied along the easy axis. Now, in that case, charged particles do what charged particles do in an electric field. They experience a force and start to move into a new equilibrium position, and that's what's happening here. The chromium 3+ ions move along this axis and move towards this oxygen 2- triangles. But you notice this B atom here moves in towards the smaller triangle. This A atom moves towards this bigger triangle. And that has a profound effect because it lifts the degeneracy between the sublattice magnetization. So the antiferromagnet, which is down, up, down, up, down, up, is no longer fully compensated, but develops a small ferrimagnetic moment, M, and that moment in the linear magnetoelectric regime is proportional to the electric field, which is mediated here by this magnetoelectric susceptibility tensor. So that is the linear magnetoelectric effect in this material, which happens once the system is magnetically ordered such that time inversion and spatial inversion symmetry are both broken, and their combined application is a symmetry operation of the system. Now, for our switching experiments, what is interesting is what happens when you apply an additional magnetic field. And if you apply an additional magnetic field, this magnetization, which we can induce by an electric field, experiences Zeeman energy, and that Zeeman energy depends on the orientation of the magnetization relative to the applied magnetic field. Now it turns out that you can have 2 distinct 180-degree domains of this chromia. One is where the spins are down, up, down, up, down, up. And the other one is where the spins are up, down, up, down, up, down. And these different domains have different signs in alpha, and therefore different signs in magnetization response on an electric field, and therefore different potential or Zeeman energies in an applied magnetic field. And if you crank up the electric field, for example, then you can determine whether a particular domain is in one state or the other state, depending on the sign of the electric field you apply. And that is depicted here. So you see basically the free energy landscape with 2 minima which are same energetic levels in the degenerate state. And then if you apply a product of electric and magnetic field, you can lift this degeneracy and make one domain state energetically favorable over the other. And what we see here in this cartoon also is something I should mention because it's important. You see here in pink some spins that point always in the same direction. This is not a material yet that I deposited on this antiferromagnet. It is a property of the antiferromagnet itself, which we call boundary magnetization. That's a robust magnetic moment that appears at the surface of materials such as chromia that have these type of symmetry conditions. That's a finding of my colleague at UNL, Kirill Belashenko, who experimentally found that these magnetoelectric antiferromagnets, when they are in a single domain state, have this robust property of boundary magnetization. Now that is what we use in a voltage-controlled exchange bias heterostructure. So here you see a cartoon where we have this antiferromagnetic system, and a ferromagnet is deposited, in our case, by molecular beam epitaxy here on top of that antiferromagnet, and there's exchange coupling at the interface between the magnetization of the perpendicular anisotropic ferromagnet and the boundary magnetization of the antiferromagnet. And now, in the presence, and that's the catch to some extent, in the presence of a magnetic field which can point in one direction, we don't have to change it, but it has to be present, we can now switch the hysteresis curve of this ferromagnet on top. There are two components to it. So whenever you have a ferromagnet exchanged coupled to an underlying antiferromagnet, you may observe the phenomenon of exchange bias, which is manifested in the fact that the hysteresis loop of this ferromagnet is shifted out of the center of this magnetization with this field coordinate system. And typically it's shifted to negative field values, and that shift we call the exchange bias field. Now in this voltage controlled system, we can switch the orientation of the antiferromagnetic interface magnetization, the boundary magnetization, and therefore we can switch whether this shift is negative or gives rise to what we call positive exchange bias. So we switch by changing the orientation of the electric field from here to here, and that you can already see can serve as a voltage-controlled building block for all kinds of voltage-controlled memory or even logic devices. And we had our first proof of principle experiments doing exactly that. They go back to 2010, where we showed particular results I refer to now. We used a single crystal, a commercially available single crystal of this material, and deposited, so macroscopic bulk, and deposited a thin film of cobalt palladium on top of it. And we could show that indeed there's this boundary magnetization which couples to the ferromagnet, and that we can switch by rotating the electric field. So as a matter of fact, what decides whether this hysteresis loop of this ferromagnet goes to the right or the left is the sign of the product of the applied fields. If the product sign is positive, we have a positive shift. If the product sign is negative, we select the different boundary magnetization, and with that we select the different shift here to negative fields. So these were these first two proof of principle results, and then we asked, of course, we got of course excited, and we were thinking about, can we make devices that potentially can replace CMOS. The easiest thing to start with is always memory, and here's a first idea what to do. So this is the fundamental building block, the physics, so to say. We have voltage-controlled magnetization of this free layer. Now you can put that into a complex or more complex structure that has a tunneling magnetoresistance structure that is made out of this layer that can be rotated, that can be switched, and a pinned ferromagnet here. And if you drive a current from here to here, then the resistance depends on the relative orientation of this magnetization. So that's a way to read out the magnetization, read out the information, the state variable that you wrote just by voltage, okay? And then you can go a step further and take this memory devices and put them into a CMOS environment and utilize the fact that they are non-volatile, so you can switch off the the electric field, switch it back on again, and the system knows the state it was in, and then you can create more complex systems such as this latch, for example. We patented a few things that is shown here. Now, if you want to do all this, you have to do it, of course, in a thin film geometry. You cannot work with bulk single crystals, and that, to get to this point, took surprisingly long. Meanwhile, of course, we got serious competition, primarily in Japan. There are multiple groups that worked and still work on this. One in Osaka, and one at Tohoku University, and So we had a bit of a race, and I show you just our results, our first results on switching in all thin film. And the publication of that result took us a very long time, but here you see it. So basically, we put first of all, we deposited a film of magnetoelectric chromium oxide or chromia on top of this palladium electrode, and we did this by pulsed laser deposition because the film is so thick. And then we deposited a small electrode of ferromagnetic material, again cobalt palladium on top, and used, it's not that small, so we could still use magneto-optics polar Kerr effect to read out the magnetic hysteresis of this ferromagnet. And as you see, if we do that with voltages between 0 and let's say -6 volt, when the system was prepared in a state of positive exchange bias, we kept positive exchange bias. But as soon as we reached that critical product value of voltage and applied magnetic field, we were able to switch the system to negative exchange bias. And that was a rather painful way to get to this point. And rather than trying to make now devices as I introduced them previously, I will report on shortcomings we identified together with our sponsors from industry, and I tell you about ways to mitigate those shortcomings of this type of devices. So what are those shortcomings despite this success? Well, one is simply the fact that you have a ferromagnet on top. And for those of you who work in the field of spintronics, you know this is where all the excitement about antiferromagnetic spintronics comes from, namely simply the fact that antiferromagnets can be switched much faster than ferromagnets. And that the reason for that is that the switching of a ferromagnet is basically tied to the Larmor precession frequency which the ferromagnet has in the presence of the applied magnetic field. And that frequency is small, giving rise to switching speeds on a nanosecond time scale, and that is too slow. And more so, this exchange bias effect is not let's say too compatible with scaling, and that's something we learned the hard way. So there are two reasons why scaling is not an easy thing in this exchange bias systems. Roughly speaking, qualitatively speaking, it is if you remove volume from the antiferromagnet, then the magnetoelectric energy that you obtain to switch the ferromagnet scales down with the volume loss, and it gets harder and harder to switch the ferromagnet. But more important is that you have this contribution to the overall total energy of the system that comes from the exchange interaction between the ferromagnet and the antiferromagnet. So in one direction of the switching, this exchange interaction is supporting the switching. In the other direction, it is hampering the switching, making it harder and harder to switch the smaller you scale the thickness of the antiferromagnet. And that's a problem because you want to have scaling possibilities. Basically, you want that your devices perform better when you make them smaller, not worse. And another major problem is, of course, that you need to have a magnetic field present to get this 180-degree switching done in this conventional magnetoelectric antiferromagnetic system. And that is something that is not good for applications. You can create, to some extent, constant magnetic field via stray fields of components of your device, but it is better to avoid it, also to avoid crosstalk between different parts in your circuits. And last but not least, the effect, as I said, requires the breaking of time inversion and spatial inversion, which both kicks in below the antiferromagnetic ordering temperature, and that means above the antiferromagnetic ordering temperature, which we call Néel temperature. You can't have this switching effect. And in chromia, that temperature is 307 Kelvin. So it is above room temperature, but slightly only. And that's for applications, in particular when you want to take these things and put it in a CMOS environment, it's not high enough. So we had to increase the Néel temperature, and that was one of our first tasks. And that's what led us to the idea that we have to change the system. And the first thing was trying to dope it with something to do that. And that's what I want to report on next. So we started out boron doping of this chromium oxide with the goal to increase the antiferromagnetic ordering temperature. And again, that was a theoretical idea that came from our colleague Kirill Belashenko, who did first principle calculations and found that by replacing the oxygen position with the boron, you can change the exchange interaction between the chromium ions, and that in turn changes the antiferromagnetic ordering temperature in favor, makes it higher. We followed this approach, so we grew boron-doped materials by pulsed laser deposition. So we start out from a chromium oxide target and we deposit in a decaborane gas background. That approach is patented here. And that works quite nicely. And indeed, we were able to increase the Néel temperature. And also nice to see was the fact that the structure of this material did not degrade. So here is a high-angle annular dark field scanning, tunneling electron microscopy image done by my colleague Paul Voils on one of our boron-doped samples. And you see nicely this buckled structure of the chromium 3+ ions here. So the C-axis goes in this direction, and you see here this tiny little bit of buckling of this chromium ion. So very, very nice structure. And then we did the next obvious thing. We said, okay, now we have increased Néel temperature. So that should give rise to, if we put that into an exchange bias system, we should see exchange bias at higher temperatures. And that was not the case, to our extreme disappointment. I show you just a few data that show this. So here we put a perpendicular ferromagnet again on top of boron-doped chromia. And you see that the loop width of this ferromagnet does get bigger once the antiferromagnetic ordering set in. That is an indication that your ferromagnet is sitting on an antiferromagnet that has ordered, and that the ferromagnet and the antiferromagnet are interacting with each other. But this interaction was not strong enough to actually pin the ferromagnet and create a sizable exchange bias. And that had something to do with the anisotropy of the system. So the boundary magnetization apparently was no longer perfectly perpendicular to the film plane. And we confirmed this by growing in-plane exchange bias system, where the ferromagnet has its easy axis in the plane rather than perpendicular the plane. And indeed, some exchange bias came back with that in that geometry. But that was not useful for us. And also, we did inverse spin polarized photoemission, showing that this material indeed is still magnetoelectric. You see that by the spin splitting here, and that the spin splitting kicks in already above 307 Kelvin. So that is good news. But it also told us that indeed the boundary magnetization is canted and not perpendicular anymore. So these were bad news for exchange bias systems. Somewhat good news was the fact that this material behaves dielectrically better. So if you grow chromia films, chromia is a very good insulator. Actually, it's used in industry often as an insulating material. But if you grow it in thin films, you suffer from defects, which are prone to leakage. And the situation improved actually by boron doping. And you see that the leakage current is lower here in the boron doped material than it is in the pure material. That was good news. So what's next? The next thing is that we observed, and that's not quite the historic pathway I show you now, but to make the story more coherent, I show you now that with the boron doping, some additional very surprising properties came up that we didn't expect. So it was not only that the system got a higher Néel temperature and that the anisotropy was slightly modified. We found something very interesting, namely that this material has can have very large electric field induced polarization. And we confirmed that and measured that by a method that is called piezo force microscopy. So that is very well known from the investigation of ferroelectric materials. So if you have a ferroelectric material, if you have ferroelectric order locally, then this ferroelectric order is always accompanied by a piezoelectric effect, meaning a local deformation of the material. And by measuring that deformation basically with an atomic force microscope, you can conclude that below was some polarization, and that allows you then basically to be sensitive on polarization. So that's what we did with these materials, and to our surprise, we found results that very much looked like a ferroelectric material. So you see here this hysteresis loop in the phase signal of this atomic force microscope. And you see this butterfly-shaped curve, which is also characteristic for ferroelectrics, in the effective in the effective piezoelectric coefficients D33 as a function of applied voltage. So it is, but however, so this almost looks as if the material became ferroelectric, but it's important to stress that it's not ferroelectric. The polarization that you create by applying an electric field relaxes when you remove the electric field. So there's no spontaneous polarization is just induced. Here you see the relaxation happening on a rather significant time scale on the time scale of a second. So it's a slow relaxation process here. And the control experiment tells us that in pure chromia, this phenomenon is absent. So there's a real qualitative change. If you compare with pure chromia, you see the data here, neither in the phase nor in the piezo coefficient, you see any significant features. So these were data taken by my UNL colleague, Alexei Gruberman. He's an expert in all things scanning probe microscopy. Now, we could speculate a little bit about what is the origin of this induced polarization. And the idea here is that we have polar nanoregions. That means regions where symmetry is locally broken and you have a relative shift of the ions relative to each other and creating local dipoles. And then if you apply an electric field, that dipole is oriented and creates polarization. Now, this is a bit more than just speculation, because again, my colleague Paul Voiles studied our boron-doped material by, as I said already, by high angular dark field electron microscopy, but also by yields and by simultaneously by density functional theory. And he found actually that these tetrahedra here, these folks here, are indeed present, and it is those that are responsible for the TN enhancement. So it's the same local regions that create the TN enhancement that create this local dipoles. Okay, now let me come quickly to the experimental data when we grow Hall bar device structures. So first of all, let me stress that what we now decided to do is, let's get rid of the ferromagnet on top. Let's not switch a ferromagnet at all. Why? Because we don't need it. We don't need it to read out in which state the antiferromagnet is. We can do that by Hall probing. By depositing a Hall cross on top of the antiferromagnet, we can actually read out the orientation of the boundary magnetization and use that to read out the state variable. And that then in turn has multiple advantages for us. We don't need exchange bias anymore. So the absence of exchange bias in boron-doped systems is not a problem anymore. We don't suffer from the low switching speeds of ferromagnets, and we basically simplify the entire device structure. Before I show you the details in boron-doped systems, let me first show you what we and others see when we do this Hall bar measurements. So we have a device like this. We have our chromium oxide sitting on a gate electrode. We deposit a Hall cross on top, and we apply a voltage across the chromia. We drive a current density through one leg of the Hall bar and measure, for example, a transverse Hall voltage across the other leg of the Hall bar. If we do that, we observe Hall resistances that have this functional form as a function of temperature, for example. Basically, what we see here, we see a fingerprint of the temperature dependence of the antiferromagnetic order parameter. So when antiferromagnetic order sets in, we see here that we see a Hall signal. And again, we can have that signal go up or down, depending on the fact whether the boundary magnetization points up or down. So that is a measurement as a function of temperature. Here you see measurements as a function of magnetic field at different temperatures, below and above and nearby the antiferromagnetic ordering temperature. And know that below the antiferromagnetic ordering temperature, the field dependence is linear and rather weak. And only above and near the chromium oxide, you get this S-shaped curves here. That is something that also becomes important in a minute. Now, it is an interesting question to ask, what is the physical mechanism that creates this Hall-like signal? I call it Hall-like because it's not a real Hall effect in the sense. So, and this question is not fully answered as of today. There are candidates. The obvious candidate would be a signal that is an anomalous Hall effect, so that you have induced magnetization in your platinum Hall bar, and that this induced magnetization originates from the boundary magnetization of the chromia. That's one possible scenario. Another scenario, and the more likely scenario, if you carefully look into these things, is a spin Hall magnetoresistance effect. And that's most likely the dominating contribution. But the take-home message here is, no matter what the effect is, what you measure is a fingerprint of the orientation of the boundary magnetization. And that brings me now to the devices which we have grown with boron-doped material. Here you see a cross-section, and here you see the optical image of the lithography we did in our Nebraska Center for Materials and Nanoscience. Here again, the same device. And now the results. So, and in particular, I like to stress the one above here. So we see, which is taken at zero applied magnetic field. No field whatsoever. Only electric fields are applied here across the boron-doped chromia. And then we see in this transverse Hall voltage, we can switch between two stable states, one that has almost zero voltage, transverse voltage, and one that has a strong non-zero voltage. And we switch between the two in a hysteretic way. Now, here you see pretty much a similar result, a switching between these two different states on applying voltages of different polarization. So we apply to play it safe, we applied here a minus 25 volt. You see that's an overkill. We could already switch with about 10 volts or so, but we wanted to make sure that we really switch. So we apply minus 25 volts, and then we switch from the zero state into a state with a sizable transverse voltage. And if we take a couple of measurements, nothing changes. But if we apply the positive voltage again, then we switch back. And we can do that over and over again in a non-volatile, reliable way. Now, if we apply a magnetic field, and that's an important insight as well, nothing changes. So that means this entire effect, this entire switching effect, as we see it here, has nothing to do with the fact that a magnetic field is present. And that tells us something. It tells us that the regular magnetoelectric effect, as we know it from pure chromia, cannot be the cause of this switching. Because we know from the linear magnetoelectric effect that a magnetic field has to be present to create this difference in the energy landscape so that you can switch with electric fields. But here we do it without an electric field. So let's have a comparison between our result in the boron doped material and results that have been done by a group in Germany some time ago in pure chromia. And here you see that this is really a different animal. So these folks have done the same thing. They have grown a Hall bar structure on top of pure chromia, and they were able to switch the antiferromagnetic Néel vector in pure chromia by applying gate voltages, as you see here. They were able to switch between different Hall resistance values by applying gate voltages. However, they always had to have a magnetic field present, actually a quite big one of the order of 1 Tesla, to achieve this type of switching. And notice also that the switching is symmetric between negative and positive resistance values. And that is very, very different in our case. First of all, we apply no field. By the way, this switching here in pure chromia is obviously a switching, symmetric switching between different Hall voltages, and that is a fingerprint of the 180-degree rotation of the antiferromagnetic Néel vector. Now, in our case, the situation is different. No magnetic field is applied. We do not switch between symmetric voltage or resistance states. We switch between almost zero and a non-zero state. And compatible with the fact that no magnetic field is applied, we think that our switching must be a 90-degree rather than a 180-degree rotation switching. And that then makes it also compatible with symmetry arguments. We do not need the magnetic field that is breaking the time inversion because we do not switch by 180 degree, we switch by 90 degree. But for the applications, that is a perfectly fine contrast, which we can of course use in devices, memory or logic. Okay, and that is a recent publication here in Nature Communications where we published this result. So we think that's a big deal because we can do that also up to 400 Kelvin. But it's a big claim also, and the big claim requires an independent confirmation, and that's what we did here. So we want to make sure that the signal we see, and in particular the switching, is indeed a switching between different magnetic states. And the first thing what we could do in our group was to look, is the behavior on a magnetic field different in this state compared to this state? So if we switch from this state into a state of non-zero Hall voltage, and we investigate the magnetic field dependence, then we get the result that virtually is none. The voltage versus magnetic field is almost flat. Very similar to chromia, pure chromia. When the pure chromia is far below its Néel temperature, it's also little to no reaction on the applied magnetic field. However, if we switch into the almost zero voltage state, we saw a rather pronounced field dependence. Here, these axes can be directly compared. They are scaled in such a way that you can directly compare them. And here we see a field dependence. And our interpretation is that this is the state where the boundary magnetization is in the plane And when we apply a magnetic field, we create a maximum torque on the boundary magnetization and start to rotate it perpendicular to the plane, giving rise to this strong magnetic field dependence. And maybe an even better independent check is a check with a completely different method. And we wanted to see if we change the orientation of the magnetization by applying an electric field, we should be able to see that in magnetic force microscopy. And again, this is what my colleague Alexei Gruberman did for us in this context. So here you see an AFM image, atomic force microscopy, so the topography of the excuse me, palladium hall bar on top of the chromia. Here, this is just this part of this hall leg in the pristine case. And below, you see the magnetic force contrast. You see what happens when we apply a positive voltage. The contrast basically disappears. When we apply a negative voltage, the contrast reappears. That was a eureka moment where we said, okay, we really switch here something that is magnetic by voltage. And my colleagues were cautious and said there is always a possibility for artifacts. So they did this Kelvin probe microscopy in addition as a cross-check to figure out if we could suffer from any charging effects that could mimic such a behavior. And the answer is no. Whether you apply a positive or negative voltage, you basically see the same Kelvin probe signal when you scan across this leg here of the hall bar. Okay, so now a few more words about this mechanism, which I sketched already a little bit. So we think what happens is the following. The substitution of the oxygen by boron creates this local polar nanoregions. And now if we apply an electric field, all these polar nanoregions are oriented in the same direction, giving rise to a macroscopic polarization of the system. And with the macroscopic polarization comes a uniform and macroscopic piezoelectric effect, a straining response, a global straining response, and which is in proportion to the applied electric field and mediated by this piezoelectric coefficient DZZ. Now this straining, in turn, gives rise to a coupling. There's magnetoelastic coupling. So by straining, you change the anisotropy, and by changing the anisotropy, you again change the free energy landscape and making one minimum preferential over the other, so that you can switch by pure electric means between an in-plane orientation of the antiferromagnetic Néel vector, but also of the boundary magnetization, between in-plane orientation and out-of-plane orientation. Now, the final remark is about switching speed. I do not have yet the experimental results, which would be extremely exciting, of course, but we have collaboration with theorists, and they were able to map the switching of an antiferromagnet basically onto a mechanical analogy here onto an inverted gravitational pendulum, and by punching in the parameters of the material parameters, they estimated that a switching speed of 100 picoseconds should be possible, which would be quite an advantage over ferromagnetic spintronic devices, and is indeed would be interesting for memory and energy efficient, non-volatile, scalable memory. So kind of what everyone wants in this context. Okay, with that, let me conclude. So I have shown that a boron doping of pure chromia changes many interesting properties in chromia. And not only is the Néel temperature increased, which is good, but we have effects on the anisotropy, and we also have this interesting phenomenon that this material suddenly reacts to an electric field by transient polarization, as you can see here again. And that can be used then in devices which allow us to voltage control, rotate the antiferromagnetic Néel vector by 90 degrees. And what is important, we can do that in zero magnetic field, and we can do that up to 400 Kelvin. So I haven't shown you these data, but this is a hysteresis loop taken at 400 Kelvin, so the effect is still present. I showed you some independent evidence that this switching is indeed a magnetic phenomenon and not an artifact. And the last remark is that the absence of spontaneous ferroelectric order may in fact turn out to be a major advantage here, because if you look at competing systems, such as multiferroic bismuth ferrite, for example, where you also have an interesting coupling phenomenon between polarization and antiferromagnetic order, these systems, their switching speed is limited by the switching of the spontaneous order parameter ferroelectricity. And we don't have that here. We have induced order, and that could mean a speed advantage. So with that, let me point out my collaborators. So that is my group at the time. Most important here, my postdoc in this context, Adam Mahmoud, who did all the lithography and the transport measurements. Will Echtenkamp, we worked for a long time on chromia. He did pioneering work and also contributed here. Mike was instrumental in getting this boron doping under control. Jun Lei, now professor in China, was a postdoc and helped us with the programming of our transport measurements. Peter Dauben did everything in terms of spectroscopy. Alexei Gruberman, as you have seen, did the scanning probe microscopy, and his group, of course. And Chalou and company did the theoretical part. And last but not least, like to thank my sponsors. And I like to thank you for your attention.
Thank you, sir, for your wonderful presentation, sir. So we have got few questions. So if you allow, we can start
Sure.
our discussion session, sir. So the first question, so what is the Néel temperature?
The Néel, what it is in general? Yeah.
Néel temperature, yeah.
Yeah. So the Néel temperature is just a technical term. The name comes from the famous physicist Louis Néel, who is basically the godfather of antiferromagnetism. And it is simply the analog to the Curie temperature in ferromagnetic systems. So where the system goes from disorder, where the spins point randomly in the different direction, into a long-range ordered state. Everyone knows it from a ferromagnet, where all spins point in the same direction below the Curie temperature, right? So all spins point in the same direction. In an antiferromagnet, the same type of phase transition happens. So you go from a random orientation of the spins into a long-range ordered orientation of the spins. The only difference is that in an antiferromagnet, not all spins point in the same direction, but they periodically point up and down, so that overall, macroscopically, the antiferromagnet has no magnetic moment, despite the fact that the spins are all ordered. And that temperature where this ordering phase transition in zero applied field happens just is called Néel temperature, in contrast to the Curie temperature. Are you still there?
Sorry, sir. There is a similar question. So what is the Néel effect?
Yeah, so I would argue what this is pointing at. This question is probably the ordering effect that's as I said, the same thing as it is in ferromagnetic materials. It's a phase transition, a so-called critical phenomenon. We are very familiar with, right? So you know these things from all kinds of phase transitions, and we know it from ferromagnets. So whenever you cool down a ferromagnet and you come to a temperature where the thermal energy K Boltzmann T and the microscopic interaction energy between the spins, which is on the order of the exchange energy, when these things become comparable, then order can start, and depending on details such as dimensionality and so forth, long-range order can happen, and that's a very exciting phenomenon. And for all applications of magnetic systems, virtually all of them, you need ordered systems. So you always need to be below an ordering temperature. So if you take your refrigerator magnet, right, that thing is below the Curie temperature. If you would heat it up, then it would lose its magnetic properties. And the same thing happens for antiferromagnets.
Okay, sir. So thank you, sir. So we have another question. So what is the polar nanoregion?
Yeah, that's a good question. So these are very local regions in the material where the perfect translational order of the system is locally broken, and you have a relative shift of the ions relative to each other, so that you create a local dipole. You know, it's very similar to if you take just molecules where the different chemical components have different electronegativity and affinity, then of course when the chemical when the molecular bond forms, the molecule often has a dipole, right? Water would be an example, right, where the oxygen grabs electric charge from the hydrogen, so that the oxygen is more charged than it should be, and the hydrogen is losing charge. That gives rise to a dipole, and that is, by the way, the reason why if you apply an electric field to water, pure water, you would have a strong dielectric material, because all these dipoles, which at first are randomly oriented, then would align in the presence of an electric field. We call that dipole orientation, and that gives rise to a very pronounced polarization. And in our chromia, something very similar happens. So you have locally this molecules, if you like, this big that have a dipole moment, and in the presence of an electric field, all these dipole moments align in the same direction and create macroscopic polarization. But but these individual local regions are small, very small, so small that you can't see them, for example, with an optical microscope. And typically they are on the length scale of a nanometer or so, and that's why they're called nanoregions, because they're on the scale of a nanometer, and polar because they have a dipole moment. So polar nanoregions means regions on a scale of a nanometer with a dipole moment.
Yeah, thank you, sir. So this may be the last question. So what is the voltage control exchange bias?
Yeah, so I mean, of course, I must admit, it's a bit special. So first one needs to understand what is exchange bias, right? So exchange bias happens when you take an antiferromagnetic material and a ferromagnetic material. Let's talk about thin films, and you bring them into close contact. Then the ferromagnet and the antiferromagnet interact at the interface. And then you get an emergent interface phenomenon, namely that the ferromagnet behaves now differently due to this interaction. And if you would measure the hysteresis loop of the ferromagnet when it interacts with the antiferromagnet, you would find that the hysteresis loop is shifted by a certain magnetic field out of the center of the coordinate system. And that shift is called exchange bias. And the magnitude of that field is called exchange bias field. Now, as the name suggests, in cases which I try to sketch, if you apply a voltage across such a bilayer structure, and if your antiferromagnetic material is very special of the type I investigate, then you can control that shift. You can move it from the hysteresis loop shifted to the left to hysteresis loop shifted to the right. And that's what we call voltage controlled exchange bias.
Yeah, thank you, sir, for your wonderful presentation and discussion session, sir. So I think our students have learned a lot of things about this method. So we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. So the main aim of our program is to motivate our students, and I think you have uh, uh, motivated our student by your lecture. So thanks
Wonderful.
again for joining
Yeah.
with us.
Thank you for doing this, and thanks. Good night, everyone.
Yeah,
Bye.
bye. Good night, sir. Have a nice day, sir.